What is de-icing for aircraft? De-icing for aircraft involves removing ice, snow, or frost from the surfaces of an airplane, particularly the wings, tail, and other critical areas. This process is crucial because ice can disrupt the smooth airflow over these surfaces, reducing lift and increasing drag, which can negatively affect the aircraft's performance and safety. How it's done. De-icing fluids. Special heated fluids, usually a mixture of glycol and water, are sprayed onto the aircraft to melt and remove ice or snow. This process is crucial for ensuring the safety of flights, especially in harsh winter conditions. The heated fluids are applied using specialized de-icing trucks that can reach all parts of the aircraft, including the wings and tail. These fluids also provide limited protection against refreezing. The glycol in the mixture lowers the freezing point of water, which helps to prevent ice from forming again immediately after the initial de-icing process. This temporary protection is vital during the time it takes for the aircraft to taxi and prepare for takeoff. Anti-icing fluids. After de-icing, a second layer of anti-icing fluid may be applied. This layer acts as a barrier, preventing ice from forming on the aircraft surfaces during the critical period before takeoff. The anti-icing fluid is designed to remain effective even in freezing temperatures, ensuring that the aircraft remains ice-free until it is airborne. This prevents ice from reforming during the time before takeoff. The anti-icing process is an essential step in maintaining the safety and efficiency of flight operations in cold weather conditions. Mechanical methods. In some cases, ice may be removed manually using brushes or scrapers, though this is less common for large aircraft. Manual de-icing is typically used for smaller planes or in situations where de-icing fluids are not available. It requires significant effort and time, but it can be effective in removing stubborn ice. Heated hangars. Parking the aircraft in a heated hangar can melt ice and snow naturally. This method is often used as a preventative measure, keeping the aircraft free from ice buildup overnight or during extended ground times. The warmth of the hangar ensures that the aircraft is ready for de-icing procedures or immediate flight without the need for additional de-icing fluids. Why it's important? Ice buildup can lead to reduced lift, which is essential for keeping the aircraft airborne. Without sufficient lift, the plane may struggle to stay in the air. Ice alters the shape of the wings, decreasing their efficiency. This can severely impact the aircraft's performance, making it harder to control and less stable during flight. Increased drag. The rough surface of ice increases aerodynamic drag. This means the engines have to work harder, consuming more fuel and reducing overall efficiency. Instrument malfunction. Ice can obstruct sensors and instruments, leading to inaccurate readings. This can compromise the pilot's ability to make informed decisions. Ensuring a clean aircraft surface before takeoff is a critical safety measure. De-icing removes ice and frost, ensuring the aircraft operates as intended. Airports in cold climates often have dedicated de-icing pads to perform this procedure efficiently, especially during winter months. These pads are equipped with specialized equipment and trained personnel to ensure the process is done quickly and effectively. Why is it important to flight safety? Let's delve into the critical reasons behind this essential procedure. De-icing is critical to flight safety because ice accumulation on an aircraft can severely impact its ability to fly effectively and safely. Ice can form on various parts of the aircraft, including the wings, tail, and sensors, each posing unique risks. Here's why. First, loss of lift. Lift is the force that allows an aircraft to rise off the ground and stay in the air. Without sufficient lift, an aircraft cannot take off or maintain altitude. Aircraft wings are designed to have a smooth surface to optimize airflow, which generates the lift necessary for flight. The shape and smoothness of the wings are crucial for maintaining this lift. Ice disrupts this smooth surface, changing the wing's shape and reducing its ability to generate sufficient lift. This can lead to a dangerous situation where the aircraft cannot achieve or sustain flight. Second, increased drag. Ice adds roughness to the aircraft's surfaces, increasing aerodynamic drag. Drag is the resistance an aircraft faces as it moves through the air, and increased drag means the engines have to work harder to maintain speed. This requires more engine power to maintain speed and can reduce fuel efficiency. The engines burn more fuel to overcome the added resistance, which can be costly and reduce the aircraft's range. Third, weight increase. Ice and snow add significant weight to the aircraft, potentially exceeding its maximum takeoff weight, which affects performance and stability. The added weight can make it difficult for the aircraft to take off and can impact its handling characteristics. Fourth, control problems. Ice on the tailplane or horizontal stabilizer can disrupt its ability to maintain proper pitch control, leading to handling difficulties or even a stall. The tailplane is essential for keeping the aircraft stable and controllable. Fifth, engine and sensor issues. Ice can block sensors such as the pitot tubes, which measure airspeed. These sensors are critical for providing accurate data to the pilots. Ice can block sensors such as the pitot tubes, which measure airspeed. These sensors are critical for providing accurate data to the pilots. Without accurate airspeed readings, pilots may make incorrect decisions that could jeopardize the flight. Inaccurate readings can lead to incorrect decisions by pilots. For example, if the airspeed is misread, the aircraft could stall or overspeed, both of which are dangerous situations. In extreme cases, ice can also damage engines by being ingested into the engine or causing imbalances. Ice ingestion can lead to engine failure or reduced performance, which is critical during takeoff and landing phases. Finally, delayed reaction in emergencies. Ice on control surfaces can reduce their responsiveness, delaying or preventing pilots from executing quick maneuvers to avoid hazards. In an emergency, every second counts, and delayed reactions can be catastrophic. Ice on control surfaces can reduce their responsiveness, delaying or preventing pilots from executing quick maneuvers to avoid hazards. This can be particularly dangerous during critical phases of flight, such as takeoff and landing. Key takeaway: without de-icing, an aircraft may struggle to take off, fly safely, or even land properly. The risks associated with ice accumulation are too significant to ignore, making de-icing an essential part of winter operations. This makes de-icing a non-negotiable step in winter operations to ensure passenger safety, crew safety, and aircraft integrity. De-icing procedures are meticulously planned and executed to remove ice and prevent its formation, ensuring that flights can proceed safely, even in the harshest winter conditions. GAP 3S. Advanced de-icing techniques include the use of infrared heating, which can quickly melt ice without the need for chemicals. Another method is the use of electrothermal systems embedded in the aircraft surfaces, which generate heat to prevent ice formation. These advanced methods are often used in conjunction with traditional de-icing fluids to ensure maximum safety and efficiency. GAP 3S. De-icing procedures can vary significantly depending on the climate. In extremely cold regions, de-icing is a routine part of pre-flight preparations. In milder climates, de-icing may only be necessary during certain times of the year. Understanding the specific requirements of different climates is crucial for maintaining aircraft safety and performance. GAP 3S. The environmental impact of de-icing is a growing concern. De-icing fluids can contaminate water sources if not properly managed. Airports are implementing more sustainable practices, such as using biodegradable fluids and recycling de-icing runoff. These efforts help minimize the environmental footprint of de-icing operations. GAP 3S. The future of de-icing technology looks promising with advancements in materials science and automation. Researchers are developing new coatings that can repel ice, reducing the need for de-icing fluids. Automated de-icing systems can detect ice buildup in real time and activate de-icing measures without human intervention. These innovations will enhance the safety and efficiency of de-icing procedures. GAP 3S. Several case studies highlight the importance of effective de-icing. In one instance, a commercial flight experienced severe icing conditions but managed to land safely due to timely de-icing procedures. Another case involved a private jet that failed to de-ice properly, leading to a runway excursion. These examples underscore the critical role of de-icing in aviation safety. GAP 3S. In summary, de-icing is a vital process for ensuring the safety and performance of aircraft in cold weather conditions. From traditional methods to advanced technologies, de-icing procedures continue to evolve. Understanding the importance of de-icing and staying informed about the latest developments can help ensure safe and efficient flight operations. Thank you for watching.